On March 15, 1976, 23 construction workers arrived at the Copper Ridge Dam site in Arizona for what appears to be another routine day of concrete pouring. By 3:47 that afternoon, 9 of them are swept away by millions of gallons of rushing water when a critical cofferdam fails catastrophically. 9 families receive the devastating news that their loved ones will never come home. 9 preventable deaths that expose a web of ignored warnings, deferred maintenance, and cost-cutting decisions that prioritize schedules over human life. All because of a temporary structure that engineers knew was operating beyond its design limits, and safety inspections that were postponed for 3 consecutive weeks to meet construction deadlines. If you want to understand how this tragedy claimed 9 lives and changed dam construction safety forever, subscribe to this channel for more investigations into preventable disasters. This episode is a fictionalized reconstruction inspired by real construction accidents and workplace safety investigations. Names, locations, and specific events have been created for storytelling purposes. The Copper Ridge Dam site sits in a narrow canyon 40 miles northeast of Phoenix, where the seasonal Agua Fria River cuts through red sandstone cliffs that rise 300 feet on either side. In March 1976, the desert air carries the constant rumble of diesel generators, the rhythmic pounding of pile drivers, and the sharp crack of dynamite blasting bedrock. Temperatures hover near 90 degrees by mid-afternoon, turning the construction site into a furnace of hot metal, concrete dust, and diesel fumes that shimmer in waves above the massive earthworks. This remote canyon represents Arizona's ambitious plan to harness the unpredictable Agua Fria River, which transforms from a dry wash to a raging torrent during spring snowmelt and summer monsoons. The completed dam will stand 180 feet high and 800 feet across, creating a reservoir to supply water to Phoenix's rapidly growing suburbs. Construction began 18 months earlier with a workforce that swells to over 200 during peak periods, making it one of the largest active construction projects in the Southwest. The work site sprawls across both sides of the river channel, connected by a temporary bridge that vibrates under the constant traffic of concrete trucks, bulldozers, and worker transport vehicles. Massive cranes tower above the construction zone, their booms swinging loads of rebar and concrete forms into position. The air thrums with the sound of compressors, generators, and the deep rumble of cement mixers working around the clock to meet aggressive completion deadlines. Workers arrive each morning before dawn, gathering at the tool sheds and equipment yards as the first light reveals the scope of the massive undertaking. The river channel has been diverted through a series of temporary cofferdams and bypass channels, allowing crews to work in the dried riverbed where the dam's foundation will be poured. These temporary structures, built from steel sheet piling, earth fill, and concrete, hold back the river's flow while construction proceeds in the exposed channel below. The project operates under intense pressure to complete the dam before the next flood season. Arizona's Bureau of Reclamation has set an October deadline for substantial completion, leaving little margin for delays or setbacks. This timeline drives 12-hour shifts, 7-day work weeks, and a relentless focus on maintaining construction schedules despite mounting concerns about equipment reliability and safety protocols. Westmont Construction Company won the contract with an aggressive bid that promised completion 6 months ahead of the nearest competitor. The family-owned firm from Denver has built 17 dams across the Mountain West over 3 decades, establishing a reputation for delivering projects on time and under budget. However, the Copper Ridge project represents their largest undertaking, stretching resources and expertise to the limits. The company's safety record shows a troubling pattern of incidents at remote construction sites. Over the previous 5 years, Westmont projects have recorded 14 serious injuries, 3 fatalities, and numerous near-miss incidents involving heavy equipment, falls, and structural failures. Federal safety inspectors have cited the company 12 times for violations ranging from inadequate fall protection to improper lockout procedures on heavy machinery. Most concerning is Westmont's history with temporary water control structures. At the Morrison Creek Dam in Colorado, a cofferdam failure in 1974 flooded the construction site, causing $2.3 million in damage and injuring 4 workers who were trapped in an excavation. The incident report identified inadequate monitoring of water levels, deferred maintenance on pumping systems, and insufficient emergency procedures as contributing factors. Despite these findings, no significant changes were made to the company's water management protocols. The regulatory environment in 1976 provides limited oversight of construction safety. The Occupational Safety and Health Administration, created just 5 years earlier, maintains only 3 inspectors for the entire state of Arizona. Federal dam safety regulations focus primarily on the completed structure's design and operation, with minimal requirements for construction phase safety measures. State authorities defer to federal oversight, creating gaps in inspection frequency and enforcement authority. Industry standards for temporary water control rely heavily on contractor judgment and experience rather than detailed engineering specifications. The American Society of Civil Engineers has published guidelines for cofferdam design, but these recommendations carry no regulatory force and are often modified based on site conditions and economic constraints. Many contractors view temporary structures as necessary evils to be built as cheaply and quickly as possible, with minimal safety margins. The Copper Ridge site's inspection records reveal a pattern of deferred maintenance and postponed safety reviews. The most recent comprehensive inspection of the temporary water control system was scheduled for February 28, but was delayed due to equipment availability. A follow-up inspection planned for March 7 was canceled when the assigned engineer was reassigned to another project. The third attempt, scheduled for March 14, was postponed again when site managers requested additional time to complete repairs on the primary cofferdam's drainage system. Training programs at the site focus primarily on equipment operation and basic safety procedures, with limited emphasis on emergency response or water-related hazards. New workers receive a half-day orientation covering hard hat requirements, tool safety, and reporting procedures, but receive no specific training on flood risks or evacuation procedures. Most crew members have never experienced a cofferdam failure and have no understanding of how quickly conditions can deteriorate when temporary water control structures fail. Economic pressures intensify as the project approaches critical milestones tied to payment schedules and penalty clauses. Westmont faces $50,000 per day in liquidated damages if construction falls behind the agreed schedule. The company has already absorbed cost overruns exceeding $800,000 due to unexpected bedrock conditions and equipment breakdowns. These financial pressures create incentives to maintain construction schedules even when safety concerns arise, leading to decisions that prioritize productivity over comprehensive risk assessment. Among the workers present on March 15 are 9 individuals who will lose their lives when the temporary water control system fails catastrophically. Site Superintendent Robert Chun, 44, brings 15 years of heavy construction experience to the project, having worked on dam projects across 4 states. His expertise in concrete placement and construction sequencing makes him indispensable to meeting the project's aggressive timeline. Chun supervises the concrete pouring operations from a platform positioned directly above the main work area. Concrete crew foreman Maria Santos, 31, leads the team responsible for placing and finishing the massive concrete pours required for the dam's foundation. Recently promoted after demonstrating exceptional skill in managing complex concrete operations, Santos coordinates between the concrete trucks, pump operators, and finishing crews to maintain the continuous pours essential to structural integrity. Her position requires constant movement throughout the active work zone, monitoring concrete consistency and placement quality. Heavy equipment operator David Williams, 39, operates the primary concrete pump that delivers mixed concrete from trucks positioned on the canyon rim to the work area 80 feet below. His experience with high-pressure concrete pumping systems makes him essential to the operation's success. Williams works from a control station positioned near the river channel, where he can monitor both the pumping equipment and the concrete placement operations. The crew includes 6 additional workers who play critical roles in the concrete operations. Pump operator assistant James Rodriguez, 26, concrete finisher Michael Thompson, 34, rebar placement supervisor Kevin O'Brien, 41, equipment maintenance technician Stephen Park, 29, concrete quality inspector Lisa Chun, 28, and general laborer Anthony Martinez, 22. Each brings specialized skills essential to the complex concrete operations required for dam construction, and each will be present in the work zone when the cofferdam fails. These 9 individuals represent the human cost of the tragedy that unfolds, but they are not merely statistics. They are skilled professionals who trust that the safety systems protecting them will function as designed. They rely on engineering calculations, company procedures, and regulatory oversight to ensure that temporary structures will withstand the forces they encounter. Their deaths will expose fundamental failures in all of these protective systems. The morning of March 15th begins with typical construction activity as crews prepare for a major concrete pour scheduled to begin at 10 a.m. The weather forecast calls for clear skies and temperatures reaching the mid-80s, ideal conditions for concrete work. River flow measurements taken at 6 a.m. show normal levels, with no indication of unusual upstream conditions that might affect the temporary water control structures. Primary cofferdam number 2, the critical structure that maintains the dry work area, shows signs of increased seepage through its base during the morning inspection. Maintenance crews note water accumulation in 3 monitoring wells, indicating higher groundwater pressure than normal. The site's chief engineer, Thomas Bradford, reviews the data and determines that pumping capacity is adequate to handle the increased flow, allowing concrete operations to proceed as scheduled. Equipment status reports indicate all major systems are operational, though several components show signs of wear that require monitoring. The primary dewatering pump experiences intermittent pressure fluctuations, and backup pumps are placed on standby to ensure continuous operation. Concrete mixing equipment operates within normal parameters, and delivery trucks are positioned to maintain the continuous pour schedule essential for structural integrity. Work assignments place the concrete crew in the lowest elevation of the construction site, directly adjacent to primary cofferdam number 2. This location provides optimal access for concrete placement, but positions workers in the area that will experience the most severe flooding if the temporary water control system fails. The work zone lies approximately 40 feet below the normal river level, creating a confined space with limited evacuation routes. Communication systems consist of handheld radios operating on 2 frequencies, allowing coordination between different work crews and supervisors. However, radio coverage in the canyon is limited by the steep terrain and interference from heavy equipment, creating dead zones where workers cannot maintain contact with the main control station. Emergency communication protocols rely primarily on air horns and visual signals, which prove inadequate when rapid evacuation becomes necessary. At 11:30 a.m., instrumentation monitoring primary cofferdam number 2 begins showing subtle changes in the structure's behavior. Piezometers measuring water pressure within the cofferdam's earth fill record a gradual increase, suggesting that seepage is increasing beyond normal parameters. Settlement monitors detect slight movement in the cofferdam's crest, indicating possible internal erosion or structural adjustment under increased loading. These warning signs remain within the ranges considered acceptable for temporary structures, and site engineers determine that monitoring should continue while concrete operations proceed. The decision reflects standard industry practice of accepting higher risk levels for temporary structures compared to permanent installations. However, the monitoring data suggests that the cofferdam is approaching the limits of its design capacity, creating conditions that will prove catastrophic within hours. By 2 p.m., concrete placement operations are proceeding smoothly, with crews maintaining the continuous pour schedule essential for achieving design strength. The concrete pump delivers material at optimal pressure and flow rate, while finishing crews work to achieve the specified surface texture and elevation. Quality control testing confirms that concrete properties meet specifications, and the pour is expected to conclude successfully by 4:30 p.m. Site Superintendent Chun coordinates the operation from his elevated platform, maintaining radio contact with crew leaders and monitoring concrete placement progress. His position provides an excellent overview of the work area, but places him directly in the path of the flood that will occur when the cofferdam fails. Foreman Santos moves continuously throughout the work zone, checking concrete consistency and coordinating between different crew members to maintain placement quality. Equipment operator Williams maintains steady pressure on the concrete pump, adjusting flow rates to match the placement crew's capacity while avoiding interruptions that could compromise concrete quality. His control station, positioned for optimal visibility of both the pump equipment and the placement operations, lies directly adjacent to the cofferdam that will soon fail catastrophically. The other crew members work throughout the confined space of the poor area, focused on their individual responsibilities and trusting that the engineering systems protecting them will continue to function. At 3:15 p.m., the first critical failure occurs when a section of steel sheet piling in primary cofferdam number 2 begins to deflect under increasing water pressure. The movement is subtle initially, detectable only through sensitive instrumentation, but it represents the beginning of a progressive failure that will prove unstoppable. Internal erosion within the cofferdam's earth fill accelerates as water finds new pathways through the compromised barrier. The failure initiates in a section of sheet piling that was damaged during installation 6 months earlier. A crane operator accidentally struck the steel sheets with a concrete bucket, creating a slight bend that was deemed acceptable for temporary service. However, the deformation created a stress concentration that weakened the steel under repeated loading cycles from fluctuating water pressure. Over time, fatigue cracking developed at the bend, gradually reducing the section's structural capacity. Seepage increases dramatically as the compromised section begins to bow outward, allowing water to flow around the sheet piling's edges. The increased flow erodes material from behind the steel sheets, creating voids that reduce lateral support and accelerate the structural failure. Pumping systems struggle to keep pace with the increasing water flow, and backup pumps activate automatically to maintain water levels in the work area. At 3:32 p.m., monitoring instruments record a sudden spike in water pressure followed by rapid settlement of the cofferdam's crest. The compromised section of sheet piling deflects beyond its elastic limit, creating a gap that allows water to flow freely into the work area. The initial breach measures only 6 inches wide, but the flow velocity through the opening begins eroding the surrounding earth fill, rapidly expanding the failure zone. Site engineers recognize that the cofferdam is experiencing a critical failure and immediately activate emergency procedures. Radio calls go out to all work crews ordering immediate evacuation of the low-lying work areas. But the confined space and ongoing concrete operations make rapid movement difficult. Workers must shut down equipment, secure materials, and navigate through congested work areas while wearing heavy safety gear that impedes quick movement. The concrete crew working in the poor area receives the evacuation order but faces significant challenges in reaching safety. Concrete hoses and electrical cables obstruct the primary evacuation route, while the continuous pour operation cannot be stopped instantly without damaging expensive equipment and compromising structural integrity. Crew members begin moving toward higher ground, but the process requires several minutes to complete safely. At 3:44 p.m., the cofferdam failure accelerates beyond any possibility of control when the initial breach expands to over 3 feet wide. Water flow through the opening reaches torrential levels, carrying away earth fill and undermining adjacent sections of sheet piling. The progressive failure spreads rapidly along the cofferdam's length as each compromised section increases loading on neighboring areas. The sound of the failure is unmistakable, a deep rumbling followed by the roar of rushing water as millions of gallons pour through the expanding breach. Workers throughout the site hear the distinctive noise and recognize immediately that a catastrophic failure is occurring. However, the speed of the failure leaves little time for effective response, particularly for those working in the lowest areas of the construction site. Primary cofferdam number 2 collapses along a 200-foot section within 90 seconds of the initial breach expansion. The steel sheet piling, designed to resist water pressure gradually applied over months, cannot withstand the dynamic loading created by the rapidly changing conditions. Each failing section increases the flow rate through adjacent areas, creating a cascade effect that destroys the entire structure within minutes. The volume of water released exceeds 15 million gallons in the first 5 minutes, creating a torrent that fills the work area faster than workers can evacuate. Water depth increases from 0 to over 12 feet within 3 minutes, transforming the construction site into a raging river carrying concrete, steel reinforcement, construction equipment, and everything else in its path. The current velocity reaches an estimated 25 miles per hour, creating forces that make survival impossible for anyone caught in the flood zone. Site Superintendent Chun attempts to coordinate evacuation efforts from his elevated platform, but becomes trapped when the structure is undermined by the rushing water. The platform, designed to support concrete operations, cannot withstand the lateral forces created by the flood and collapses into the torrent. Chun and two other supervisors on the platform are swept away by the current and disappear beneath the surface within seconds. Foreman Santos and 4 crew members working in the main pour area find their evacuation route cut off when the flood reaches the access ramp leading to higher ground. The water level rises too quickly for them to reach safety, and the powerful current makes swimming impossible even for strong swimmers. Heavy work boots, tool belts, and safety equipment that normally protect workers become deadly burdens that drag them beneath the surface. Equipment operator Williams remains at his control station attempting to shut down the concrete pump and prevent equipment damage when the flood reaches his position. The control station, positioned for optimal visibility of the work area, lies directly in the path of the rushing water. Williams is swept away along with the concrete pump and associated equipment, carried downstream by currents that exceed the strength of any individual to resist. The 6 remaining crew members working throughout the pour area face similar circumstances as the flood transforms their workplace into a death trap within minutes. The confined nature of the work zone, surrounded by steep canyon walls and construction equipment, provides no escape routes when water levels rise rapidly. Heavy concrete forms, reinforcement steel, and construction materials become deadly projectiles carried by the current, creating additional hazards beyond the drowning risk. Emergency response begins immediately as site personnel recognize the scope of the disaster unfolding below them. Radio calls summon emergency services from Phoenix and surrounding communities, while site crews begin organizing rescue efforts for any survivors who might be swept downstream. However, the speed and violence of the flood leave little hope for immediate rescue of those caught in the initial failure zone. The flood continues for over 2 hours as the compromised cofferdam allows the river to reclaim its natural channel through the construction site. Water levels gradually recede as flow rates stabilize, revealing a scene of complete devastation where the active work area once stood. Concrete forms, heavy equipment, construction materials, and personal belongings lie scattered throughout the canyon, carried hundreds of yards downstream by the powerful current. Search and rescue operations begin as soon as water levels drop sufficiently to allow safe access to the affected area. Emergency responders from Phoenix Fire Department, Arizona Department of Public Safety, and local volunteer rescue units arrive with specialized equipment for water rescue and recovery operations. The challenging terrain and ongoing hazards from unstable debris complicate rescue efforts and require careful coordination to prevent additional casualties. Recovery teams work systematically downstream from the failure site, searching for survivors and victims among the debris scattered throughout the canyon. The powerful current has distributed materials over a 3-mile stretch of the river channel, requiring extensive search efforts to locate all missing personnel. Specialized dive teams arrive to search areas where deep water might have trapped victims beneath debris or in underwater cavities. The immediate aftermath reveals the full scope of the tragedy as rescue teams account for all personnel who were present at the site when the cofferdam failed. 9 workers are confirmed missing and presumed dead, swept away by the flood when the temporary water control structure collapsed catastrophically. Search efforts continue for several days, but the violence of the flood and the rocky terrain downstream make recovery of victims extremely difficult. Among those who lose their lives are Site Superintendent Robert Chun, Foreman Maria Santos, Equipment Operator David Williams, and 6 crew members who were working in the pour area when the flood struck. All 9 individuals are overcome by the rushing water and debris before they can reach safety, despite immediate recognition of the emergency and attempts to evacuate the work area. Their deaths represent a devastating loss of experienced construction professionals and highlight the extreme hazards associated with temporary water control structures. The accident scene reveals the massive forces involved in the cofferdam failure and flood. Concrete trucks weighing over 30 tons are moved hundreds of feet from their original positions, while steel reinforcement bars are bent and twisted by the current's power. The concrete pump, weighing approximately 15 tons, is carried over 400 yards downstream and buried beneath tons of debris, illustrating the flood's incredible destructive capacity. Environmental impact extends well beyond the immediate construction site as the flood carries concrete, fuel, hydraulic fluid, and other construction materials downstream into the Agua Fria River system. Approximately 2,000 gallons of diesel fuel and 800 gallons of hydraulic fluid contaminate the waterway, requiring extensive cleanup efforts to prevent long-term ecological damage. The Arizona Department of Environmental Quality initiates emergency response procedures to contain and remediate the contamination. The construction project suffers damage estimated at over $12 million, effectively destroying 18 months of work and requiring complete reconstruction of the temporary water control system. All major equipment positioned in the work area is either destroyed or severely damaged, while completed concrete work must be demolished and rebuilt due to contamination and structural damage from the flood. News of the tragedy spreads quickly through Arizona's construction industry and beyond, generating intense media coverage and public scrutiny of dam construction safety practices. The loss of 9 lives in a single industrial accident represents one of the worst construction disasters in Arizona's history, prompting immediate calls for improved safety regulations and oversight of temporary structures used in dam construction projects. Family members of the victims faced the devastating reality of sudden loss, with 9 households forever changed by the preventable tragedy. Wives become widows, children lose fathers, and parents bury their adult children due to failures in engineering judgment, safety protocols, and regulatory oversight that should have prevented the disaster. The human cost extends far beyond the construction site to encompass entire families and communities affected by the loss. The investigation into the fatal cofferdam failure begins immediately, led by the Arizona Division of Occupational Safety and Health in coordination with federal agencies, including the Bureau of Reclamation and the Army Corps of Engineers. The investigation team includes structural engineers, geotechnical specialists, construction safety experts, and forensic investigators with expertise in analyzing catastrophic failures of temporary structures. Investigators work methodically to reconstruct the sequence of events leading to the 9 deaths, examining physical evidence, reviewing construction records, interviewing survivors, and analyzing the failed cofferdam's design and construction. The investigation focuses on determining why the temporary structure failed so catastrophically and whether the deaths could have been prevented through different design, construction, or monitoring practices. Physical examination of the failed cofferdam reveals multiple contributing factors that led to the catastrophic collapse and resulting fatalities. The steel sheet piling shows evidence of fatigue cracking that developed over several months of service, weakened by the installation damage that was never properly repaired. Soil analysis indicates that the earth fill used in the cofferdam's construction contained more clay than specified, reducing its stability and increasing susceptibility to internal erosion. Geotechnical investigation reveals that groundwater conditions at the site were more challenging than anticipated during the original design process. Higher than expected water pressure placed additional stress on the cofferdam structure, contributing to the gradual weakening that eventually led to catastrophic failure. The investigation determines that more comprehensive subsurface investigation during design could have identified these conditions and led to a more robust cofferdam design. Construction records review exposes significant deficiencies in quality control and monitoring procedures that contributed to the fatal outcome. The damaged sheet piling was noted during construction but was not properly repaired because of schedule pressures and cost considerations. Monitoring instruments were installed but not calibrated properly, providing misleading data about the cofferdam's actual condition in the days before the failure. Engineering analysis demonstrates that the cofferdam was operating beyond its design capacity for several weeks before the catastrophic failure. Water levels had increased due to upstream snowmelt, placing higher loads on the temporary structure than originally anticipated. However, no formal engineering evaluation was conducted to assess whether the increased loading exceeded safe limits, representing a critical failure in professional judgment. Expert testimony during the investigation reveals that industry practices for temporary water control structures were inadequate for ensuring worker safety during major construction projects. The tendency to build cofferdams as cheaply as possible, with minimal safety margins, creates conditions where small problems can escalate into catastrophic failures that claim multiple lives. The investigation concludes that more rigorous design standards and monitoring requirements are essential for preventing similar tragedies. Medical examiner findings confirm that all 9 victims died from drowning, with several also suffering severe trauma from debris carried by the flood. The violence of the failure left no opportunity for survival once workers were caught in the rushing water, emphasizing the importance of preventing such failures rather than relying on emergency response to save lives. The speed of the flood made evacuation impossible once the cofferdam began its final collapse sequence. Root cause analysis identifies the primary cause of the fatalities as the catastrophic failure of primary cofferdam number 2, which was operating beyond its design capacity due to increased water loading and was weakened by construction damage that was never properly repaired. Contributing factors include inadequate monitoring, deferred maintenance, schedule pressures that prevented proper repairs, and insufficient emergency planning for cofferdam failure scenarios. The investigation determines that the deaths were preventable through several different interventions. Proper repair of the installation damage would have maintained the sheet piling's structural integrity. More comprehensive monitoring would have detected the developing failure in time to evacuate workers safely. Better emergency procedures could have enabled faster evacuation when the failure began. Most importantly, more conservative design with adequate safety margins would have prevented the failure entirely. Multiple perspectives emerge during the investigation as different parties attempt to assign responsibility for the tragedy. Westmont Construction argues that the failure resulted from unforeseeable geological conditions and extreme weather that exceeded design parameters. The engineering firm responsible for cofferdam design maintains that their work met industry standards and that construction defects caused the failure. Federal regulators contend that existing standards were adequate but were not properly implemented. The detailed investigation findings, released 8 months after the tragedy, conclude that the 9 deaths resulted from a combination of inadequate design standards, poor construction practices, insufficient monitoring, and regulatory gaps that allowed dangerous conditions to persist. The report makes 17 specific recommendations for preventing similar tragedies, ranging from improved design requirements to enhanced emergency procedures and more frequent inspections of temporary structures. Legal proceedings arising from the 9 deaths begin within weeks of the tragedy as families file wrongful death lawsuits against Westmont Construction, the engineering firm, and other parties involved in the project. The lawsuits allege negligence, inadequate safety measures, and failure to protect workers from known hazards associated with temporary water control structures. Legal discovery reveals internal documents showing that some parties were aware of elevated risks but failed to take adequate protective action. Criminal negligence charges are filed against 3 Westmont supervisors, including the project manager who authorized continued work despite known problems with the cofferdam. Prosecutors argue that the decision to maintain construction schedules while deferring critical repairs constitutes criminal negligence that directly contributed to the 9 deaths. However, proving criminal intent in complex engineering failures proves challenging, and the charges are eventually reduced to regulatory violations. Civil lawsuit settlements eventually total over $8.5 million paid to victims' families, with Westmont Construction bearing the largest share of liability. The settlements include provisions for ongoing support for victims' children and spouses, recognizing that the financial impact of the deaths extends far beyond immediate funeral expenses. Insurance companies initially resist coverage claims, arguing that the failures resulted from criminal negligence not covered by standard policies. Regulatory changes prompted by the 9 deaths include new federal requirements for temporary water control structures used in dam construction. The Department of Labor establishes specific design standards, monitoring requirements, and inspection frequencies for cofferdams and similar temporary structures. These regulations mandate professional engineering oversight, regular safety inspections, and emergency procedures specifically addressing potential structural failures. The Bureau of Reclamation revises its construction specifications to require more conservative design margins for temporary structures, recognizing that the consequences of failure often exceed those anticipated during initial design. New requirements include redundant monitoring systems, formal engineering review when conditions change, and mandatory worker training on emergency procedures related to water control system failures. Arizona implements state-level regulations requiring enhanced safety measures for construction projects involving temporary water diversion. The new rules mandate daily inspection of critical temporary structures, immediate engineering review when monitoring data indicates changing conditions, and evacuation procedures that can be implemented within minutes when structural failures begin. Penalties for violations include criminal charges for supervisors who knowingly allow unsafe conditions to persist. Industry-wide changes include development of new professional standards for temporary structure design and construction. The American Society of Civil Engineers establishes a committee on temporary construction safety, developing guidelines that emphasize worker protection over cost minimization. Professional engineering societies implement continuing education requirements focused on construction safety and the legal responsibilities of engineers for protecting worker lives. New safety technologies emerge from the tragedy, including real-time monitoring systems that can detect developing structural failures and automatically activate warning systems. Advanced instrumentation provides continuous monitoring of critical parameters, with alarm systems that alert workers immediately when conditions exceed safe limits. Automated evacuation systems use air horns, flashing lights, and radio broadcasts to ensure that all personnel receive emergency warnings regardless of their location within the construction site. Compensation for victims' families extends beyond legal settlements to include ongoing support programs and memorial scholarships. The Arizona Construction Safety Foundation, established in memory of the 9 victims, provides educational scholarships for children of construction workers and funds safety research aimed at preventing similar tragedies. Annual memorial services honor the victims and remind the industry of the human cost of inadequate safety measures. The Copper Ridge Dam project eventually resumes under new management with significantly enhanced safety protocols and a completely redesigned temporary water control system. Construction takes an additional 14 months to complete, but the project proceeds without further serious incidents due to the comprehensive safety improvements implemented after the tragedy. The completed dam includes a memorial plaque honoring the 9 workers who lost their lives during its construction. Long-term impact on the construction industry includes fundamental changes in how temporary structures are designed, built, and monitored during major projects. The 9 deaths at Copper Ridge serve as a watershed moment that forces the industry to acknowledge that temporary does not mean disposable when human lives are at stake. Professional standards now require the same level of engineering rigor for temporary structures as for permanent installations when worker safety is involved. Safety culture within the construction industry evolves significantly in response to the tragedy, with greater emphasis on worker protection and hazard recognition. Training programs now include extensive coverage of water-related hazards and emergency procedures, ensuring that workers understand the risks associated with temporary water control systems. Safety meetings regularly discuss the Copper Ridge incident as an example of how quickly conditions can become fatal when protective systems fail. Current dam construction projects incorporate lessons learned from the 9 deaths through enhanced monitoring, redundant safety systems, and comprehensive emergency procedures. Modern cofferdams include multiple backup systems, real-time structural monitoring, and automated warning systems that provide immediate notification when conditions become dangerous. The cost of these safety improvements is considered essential rather than optional, reflecting the industry's recognition that no construction schedule is worth human lives. How families of the victims are remembered varies, but their loss continues to influence safety practices decades later. Maria Santos' husband establishes a foundation providing safety training scholarships, ensuring that future construction workers receive better preparation for recognizing and responding to hazardous conditions. Robert Chin's children pursue engineering careers focused on construction safety, carrying forward their father's commitment to protecting workers through better design and procedures. The technical lessons learned from the fatalities continue to inform engineering practice and regulatory requirements. Professional engineers now understand that temporary structures require the same level of analysis and monitoring as permanent installations when failure could result in loss of life. Design standards mandate adequate safety margins, redundant protective systems, and comprehensive monitoring to ensure that developing problems are detected before they become catastrophic. Prevention measures developed in response to the 9 deaths now represent standard practice throughout the construction industry. Real-time monitoring of temporary structures, formal emergency procedures, enhanced worker training, and regulatory oversight have become routine elements of major construction projects. While these measures cannot eliminate all risks, they significantly reduce the likelihood of similar tragedies occurring in the future. The legacy of the 9 workers who lost their lives at Copper Ridge extends far beyond the specific circumstances of their deaths. Their sacrifice led to fundamental improvements in construction safety that have prevented countless additional fatalities on projects throughout the world. Professional engineers, safety specialists, and construction workers continue to study the incident as a reminder of their responsibility to prioritize human life over schedule and cost considerations. The Copper Ridge tragedy teaches profound lessons about the consequences of treating safety as secondary to productivity and the devastating impact when professional judgment is compromised by economic pressures. 9 skilled workers trusted that the engineering systems protecting them would function as designed, that their employers would maintain safe working conditions, and that regulatory oversight would prevent dangerous situations from developing. Their deaths reveal how quickly that trust can prove fatal when multiple protective systems fail simultaneously. These were not just statistics in a safety report, but individuals with families, dreams, and futures that were cut short by preventable failures in design, construction, and oversight. Robert Chen's 15 years of experience could not save him when the platform he trusted collapsed beneath him. Maria Santos' recent promotion to foreman could not protect her when the work area she supervised became a death trap. David Williams' expertise with heavy equipment meant nothing when the flood swept away his control station and everything around it. The human cost extends beyond the 9 workers who died to encompass their families, friends, and colleagues who must live with the knowledge that these deaths could have been prevented. Children grow up without fathers, spouses face the future alone, and parents endure the unnatural grief of outliving their children. The construction industry carries the collective responsibility for these losses and the obligation to ensure that similar tragedies never occur again. Professional vigilance remains the most important lesson from Copper Ridge, recognizing that safety systems require constant attention and maintenance to protect the lives they are designed to preserve. Engineers must resist pressures to compromise safety margins. Contractors must prioritize worker protection over schedule adherence, and regulators must maintain oversight that prevents dangerous conditions from developing. The price of complacency is measured in human lives that can never be recovered. The 9 workers who died at Copper Ridge Dam deserve to be remembered not just as victims of a tragic accident, but as individuals whose deaths led to fundamental improvements in construction safety that continue to protect workers today. Their legacy lives on in every safety regulation, monitoring system, and emergency procedure that prevents similar tragedies from claiming additional lives. In their memory, the construction industry maintains its commitment to ensuring that every worker returns home safely at the end of each day. If this story about preventable tragedy and lost lives gave you insight into why safety matters in construction, leave your like and share with others who appreciate learning from fatal accidents so that others might live.